Okay, well, good morning. We'll continue our discussion about the high-frequency analysis of circuits today. So just quickly recapping what we went over last time. So what we did last time, we analyzed the first-order system. So we saw that for the first-order system, where you basically had a system with no dynamics inside, and a single input, single output, and one reactive element, one energy storage element, which could be an inductor or a capacitor. So I'm just showing you the capacitor, but it could be an inductor. That's called C1. We derived the transfer function for this, and when we derive this for general transfer function, the most general case, it's basically h of s, by definition, of course, the y of s divided by x of s, is going to be h0, h naught, plus h1 tau s, divided by 1 plus tau s, where h0 and h1 were what we call transfer constants. So h0 is the zero value transfer constant, and h1 was the infinite value transfer constant in this case for C1. And the superscripts indicate, basically the superscripts always, in this notation, the only thing they indicate is the index of the element that's being in infinite value. And when it's zero, it means that everything is zero value. No reactive element is infinite value. So there are two transfer constants and one time constant, tau. Tau, which is basically the time constant associated for the reactive element. The way you determine that was basically by setting all independent sources, nulling all independent sources, and basically looking at them and looking at the resistance seen by the capacitor. So if it's a capacitor, so let's say the resistance seen across this port, let's call this R naught. And if it's R naught, if you have a capacitor, this time constant would be R naught C1. And if it's an inductor, it would be L1 over R naught. So this is what you really need to know. And we derived this, so we are not going to derive it again, to determine the transfer function of first-order systems. And this is a very useful and important result. You will see that it can actually get you a lot of information just by looking at this first-order result, and then we'll do more elaborate ones as we go forward, and we see what we can learn from higher-order ones. But we can learn quite a bit from this even first-order one. Okay, so, and then basically we looked at several examples, right? Let's quickly go over a couple of examples here. So we did some basic examples with resistors and inductor and resistor and capacitor, just for you guys to get a feel. But then the other example we did, and I'm going to quickly redo it, spending less time on it, was a follower. A source follower, a common drain stage. R1 and R2 in general. And let's say in this case we said since we are so far we can only do first order systems, we can do C pi or C mu, we can do them one at a time. And then we'll do both at the same time, and we'll do nth order stuff and all this thing, and we'll see what happens. So for the time being, we are just doing C first order. So for first order analysis, if you assume that this is C pi, the only thing you have, if I were to determine the transfer function, how do I do it? Well, I say I need to know two transfer constants and one time constants for a first order system. Let's determine our transfer constants. The transfer constants, so H naught, which is the zero value transfer constant, is when C pi is zero, meaning it's an open. If it were an inductor, it would be a short. So if it were an open circuit, what happens? What's the gain of the stage? Well, if in doubt, you can always look at the equivalent model. In this case, I'm going to use a T model. So since this current is 0, because this is IS and this is IS, this current is 0, therefore this voltage is the same as that voltage, therefore you have just simply a voltage divider here, right? Which basically tells you that it's going to be R2 over Rm plus R2. Some basic stuff you've done quite a bit before, several times. And then H1, which is the infinite value time constant in this, is transfer constant in this case. We have to determine when C pi is shorter. Now, in this case, I don't make a distinction of what infinite value, which infinite value transfer constant it is, because there's only one element. So it's unambiguous when I say it's infinite value transfer constant that it's this element. But if I have more than one, then I have to say which one it is. And you can imagine, in this case, if I have two elements, 1 and 2, H1 is going to be when 1 is infinite value, and H2 is going to be when 2 is infinite value, and H1, 2 is going to be when both of them are infinite value. So just like a little look ahead. So, well, instead of calling it H1, really, you can call it H pi to make it even more specific because it's the C pi, so we use the same index. And if I short circuit this, basically, this transistor is irrelevant because this becomes 0, this current becomes 0, this becomes 0. So I have R1 and R2. It's a voltage divider there, R2 over R1 plus R2. And then I have to determine the time constant. And then we did the analysis explicitly. We applied the voltage source and current source, but we can also use the results that we did in one of your homework sets. And I'm going to restate them here quickly, just for future reference. So from now on, we will use them more and more often. So the results were, I think it was in homework 3 problem, homework 5 problem 3, something like that. So if this is R1, R2, and R3, and I'm not sure if I'm keeping the same numbers as the homework. Okay, good. Oh, so if you have a MOSFET, but let's do it bipolar, and then we'll see how it reduces for MOSFET, because bipolar has more terms essentially. So the resistance seen, so we have 3 resistances, right? So now it's obvious why I would call this R pi and capital R pi, and this one R mu, and this one I can call R theta. Okay. So we had you have derived these, so I'm just going to state these and help me out, make sure I don't make mistakes. So R pi is R pi of the transistor parallel with the 2 resistors connected to this 2 terminal. The total resistance you see across it, R1 plus R3, over 1 plus GM R3. And R mu was written as R left plus R right plus capital GM R left, R right. And these are good results to know because R left, so there are intermediate variables, R left essentially is the resistance you see from this node to ground, to the left of it, to ground. What is that resistance? You see R1 parallel with the input resistance of the stage, which is R pi plus 1 plus beta times R3. So it's R1 parallel R pi plus 1 plus beta R3. And R right is again the resistance from the right hand side to ground. If you ignore RO, it's going to be R2. If you don't ignore it, it will be R2 in parallel with whatever output resistance of the stage is. So I'm just going to ignore R2 for simplicity, RO for simplicity. So in this case, it becomes simply R2. And GM, capital GM, is the effective GM, which is basically lowercase gm, divided 1 plus GM R3, reduced by the degeneration factor. Or better yet, you can write it as 1 over Rm plus R3. I like it better that way. So that was R mu. And R theta, so R theta, it had some other terms for beta and all those things, but I'm going to use just the approximation one, which is a good approximation as long as beta is large. which is again the two resistors we have across here, R2 and R3, R2 plus R3 divided by 1 plus GMR. And for MOSFETs this is exact because beta is infinity, so anything you have anywhere you have beta or effective beta, that would disappear in a MOSFET, because in a MOSFET for instance R pi is infinity. So this disappears, it's just that. That's exact in a MOSFET, and here also you basically don't worry about this. The R left is going to be just R1, because this term is going to be infinity. It's beta dependent. I'm sorry, it's going to be R1 parallel R3.
That's R1.
I'm sorry?
That's R1, right?
Beta is infinity, but 1 is not infinity.
But R3 goes in.
Oh, no, that's right. It's going to disappear. Sorry, you're right, actually. All of it's going to disappear. So it's simply R1. You're right. So, once again, it's basically R left is simply R1 in the case of a MOSFET, and R right would be R2. Okay, and GM would be scaled by the same factor. So, these are good results to remember. And I've strategically placed them someplace I have to cover. So, now if I use those results, then it becomes a rather trivial matter, right? What is the resistance seen across here?
R1 plus R2.
It's R1 plus R2 divided by
1
plus GMR2, right? So it becomes R1 plus R2 divided by 1 plus GMR2 in this case, which basically I can write as Rm. Multiply numerator and denominator by Rm. Okay. So these are the three parameters that you need to determine for this guy. And once I have these three, basically I'm done. So we can use that expression to write our transfer function that we had earlier. And when we did that, we came up with the following transfer function. So the H0 part has to be there. A lot of times you're better off just writing it as H0, because you know what H0 is, it makes your life easier. So let's do it that way. And then we have 1 plus and 1 plus here. The denominator you have 1 plus this combination.
You forgot the C.
C, correct, you're right. I have that C pi here and C pi. So let's call this R naught. So it's R naught C pi. And in the numerator, you saw easily it was Rm C pi. Correct?
Yes.
Alright. So, and we saw that we have a pole and a zero. Right? What's the pole frequency? It's 1 over this time constant. Minus that, exactly. P is minus 1 over R naught C pi, which you can expand in this form. You can basically write it as 1 over Rm C pi times Rm plus R2 over R1 plus R2. And Z is going to be minus 1 over Rm C pi, which you can also sometimes rewrite it Gm over C pi. That's a more common way of writing it in the literature, so that's fine. And the reason that you write it like this because it reminds you of FT of the transistor, right? It's a little bit higher than FT of the transistor because it doesn't have CMU, but it's on the order of the FT, so this is like omega T more accurately. So this is a little bit higher, so let's say approximately close to omega T, and this is also close to omega T, so it's minus omega T scaled by Rm plus R2 over R1 plus R2. So what you see is that where the relative position of the pole and zero is determined really, the relative position of the pole and zero, which one happens first, determined by relative values of Rm and R1, right? So if R1 is greater than Rm, what's going to happen is that your zero will happen before your pole, right? So what that means in the frequency domain on a Bode plot for the pointing log of the transfer function, you see that you have the zero and then you have the pole. So you have the amplitude goes increase, the magnitude increases. Which again makes sense because you're starting from this value, and then you end up at that value. You start from this value and you end up at that value. So, and what happens to the phase? Well, that determines on whether or not your left half plane or right half plane goes. Well, the pole is left half plane because the root of the denominator is negative, and so is the 0. It's also a left half plane 0. So they're both on the same half plane. So it's a minimum phase.
It's vice versa because
Okay, hold on. Yeah.
that's the case. One is the smaller number.
So let's see. So at low frequency we have basically R2 over Rm. And this is R2 over R1 plus R. So if R2 is greater than Rm, what happens is that this value becomes smaller. Smaller. Right? Okay. So we have to determine which one is larger. So basically this is the situation that happens when you have. And the phase, of course, so this increases the phase a little bit. The 0. So you have positive phase here and then negative phase back. It's a minimum phase system. Okay. Now, and if the opposite is true, so you have a response that looks like this. If you have R1 greater than Rm, then you have this pole and a 0, and then you basically have something that looks like that, and the phase looks like that. So, in this range, what does it look like? This output. It looks like an inductor. Right? And in this range, it looks like a capacitor. So what do we say about these? What can you say? What can we do about it? So why is that inductor important, if you're going to think about it? Actually, this is not really the, well, it kind of like, it's a transfer function, right, at this point. So you don't really, it looks like something increasing with the frequency, but it basically, the transfer function of this state looks like that at this state, this point. So it goes up, depending on, or down, but more or less, you see, it doesn't change that much. If R1 and Rm are not that different, so it can actually remain relatively constant. So what does that tell you? That tells you that the stage, as shown, has a relatively flat response. So it's not frequency limiting very quickly. And you will see part of it is because it doesn't have a lot of gain. Now, can a stage have large gain? According to this, it can have very large gain up to infinity, right? Can it have such large gain at infinity? No. Why is that? Why do we see that? Because we've limited, our models are limited, right? What haven't we modeled? We have, for instance, we haven't modeled C mu. And if I put the C mu there, then we'll have another pole because of that, and we'll see what happens when we get to multiple. Now, the other interesting question about this guy is its output impedance. So to determine its output impedance, we need to look at this, basically. Because that's the intrinsic output impedance. Whatever you see other than that is basically going to be in parallel. Whatever you see there is going to be in parallel with R2. So what is this output impedance? So let's say I'm interested in determining Z out. So let's do it here, perhaps. So I'll reduce the stage of interest to this. Let me just even draw the small signal model. And I want to know what's the impedance looking into here when I have a capacitor C pi. So I can do two things. I can determine my impedance or admittance. And I'm going to do both now. Right? Just so that you guys see it one time. But that shows you, and to show you how things would be different if you don't, if you calculate one from the other, and how the end result would be the same. So let's do the impedance first. what is the transfer? What are the? I have to determine two transfer constants and one time constant. What are the transfer constants? What is Z naught? Z naught is the impedance you see when C pi is 0. What do you see? What is the impedance looking into here?
1, so that's Rn.
It's Rn. Correct. What is Z pi? It's the impedance you see when C pi is infinity. It's shorted. What is it? Take it?
R1.
R1, correct. Now, and what is tau? The time constant, the resistance seen by this guy, what does it see? Well, when I'm nulling all my independent sources. So this independent source will be open. So if I have an open circuit there, then what is the resistance I see? Rn. So, and if the resistance is Rm, so tau pi and Rm C pi. So let's put the three of them together. I see Z of S would be Rm plus R1 Rm C pi S divided by 1 plus Rm C pi S. So I factor Rm, so it's Rm times 1 plus R1 C pi S divided by 1 plus Rm C pi S. Again, you see a pole and a zero in the transfer function. But this is different. These are definitely different poles. I mean, you see from the one that we calculated for the transfer function itself, the gain transfer function, it had the same zero, but it had a different pole. The zero of that is the same pole of this guy. So it doesn't necessarily, they don't have to be necessarily the same. So that's Z. How about Y? Let's calculate Y. The admittance. To calculate the admittance, what do you need to do? You need to put a voltage source here. Right? And measure Ix. So what would be the same and what would be different? So let's calculate. So I have to calculate Y naught, which is the impedance looking into here. Admittance, the conductance looking into there. Right? When C pi is 0, which is what? 1 over Rm, so Gm. What is Y pi when C pi is shorted is 1 over R1. So those two seem to behave the same way as these two. How about tau? It's called tau prime. What is the time constant? Well, I have to null my independent sources. This time I have a voltage source, so I have to short it. If I short the voltage source, then what is the resistance you see across here? What do you see looking this way? This is ground. What is the resistance you see looking this way? Infinity. Right? You're looking into the gate. The short. What do you see this way? R1. So it's R1 C pi, which is different from this one. So you get a different time constant, alright? But let's see what happens. So let's put all of them together. So Y of S is Gm plus 1 over R1 times R1 C pi S divided by 1 plus R1 C pi S. So multiply the numerator and denominator by Rm. And so let's actually just directly write 1 over Ys. So 1 over Ys and then multiply the numerator and denominator by Rm. You can see Rm times 1 plus R1 C pi S, the denominator of that. Rm will cancel that Gm plus Rm C pi S, which is the same as Z of S. Right? Had I used this source, the voltage source, for calculating the impedance, I would have got the wrong time constant, and as a result, I would have got the wrong result. Because I was not really calculating an impedance when my stimulus is a voltage source. I'm calculating an admittance. But if I keep them consistent, I get the correct result either way. Sometimes this is more convenient, sometimes the other one is more convenient. So you have a choice. But you have to stick to your choice from the beginning to the end. And be consistent. And you realize that the stimuli definition matters because it determines whether or not you open it or short it, and that will change the time constants. Does this make sense? Good. Okay. So, and then the other thing that we saw about this stage is that, okay, well, let's see this, if this is our, so now, one way or another, this is our transfer function.
A quick question is to make sure. Sure. So it only matters what we have to say. I understand we have to stay consistent between a voltage or a current source, but it only matters because of how we calculate power, right? I mean, in this methodology, we say null the independent sources versus if you were to apply brute force KCL on this, it doesn't matter which one you put, right?
No, it wouldn't matter. No.
Right. So it's the methodology that requires us to be consistent with what we put.
Well, in general, the response of the system is dependent on the kind of stimuli that you apply to it.
Right.
When you say I apply brute force KCL, basically you're saying that I know this voltage and I know this current in a sense.
Right.
The voltage is Vx and the current is Ix. So you're basically using the substitution theorem there to force that condition. So when you're using brute force KCL or KVL, it doesn't matter because you're forcing it. But you know, that's for instance one difference between the Z parameters and Y parameters and the S parameters. Right? The Y parameters are not, the Y11 is not exactly just 1 over Z11 in a two-port, for example, if you talk about it. The reason is that what is connected to the other port matters. Because in a Y parameter calculation, you have one kind of impedance, and in the Z parameter, you have a different kind of impedance. Right? So that matters. But yes, I mean, if you were applying brute force KCL or KVL in the sense of applying voltage source and measuring the current source, that doesn't matter. Okay?
Yeah.
Any other questions? Alright, so let's take this stage, and so we calculated the output impedance. So we said the output impedance of this stage looks like is Rm1 plus R1 C pi S divided by 1 plus Rm C pi S. And again, we can look at this characteristic impedance and see how it looks. Again, so basically we're looking at 20 log of Z of j omega versus log of omega on a Bode plot. So two cases, this is simpler to follow, all right? Because if Rm is smaller than, it's at very low frequencies, what is it? It's Rm. And at higher frequencies is R1. At very high frequencies, because C pi is going to be shorted, right? So we know that already. We know Z of 0 is Rm, and Z of infinity is R1. So if R1 is greater than Rm, then it will do this. You know, that's another way of saying that is basically that you have a pole. You have a 0 and then you have a pole. First we have a 0. Both of them are left calculated. And if the opposite pole happens, in other words, your Rm is smaller than greater than R1. In other words, when you have really small R1, then it comes like that. So now this impedance here looks inductive, right? This is an impedance now. What kind of thing is an impedance that grows in frequency? Well, in this range, it looks inductive. And in this range, it looks capacitive. Now, for this to hold, R1 has to be really small. Usually the impedance of what drives the stage, this is a more typical case, although this can happen too. And that's why a lot of times they say the output impedance of a source follower or common drain is inductive. It's not necessarily always inductive, but for some typical numbers, it usually becomes inductive. And this can be a problem because then in conjunction with the capacitance of the following stage, it can create a resonance. It can create an LC parallel combination. Now, what is the equivalent model for this, if you want to think about it? What kind of stage would give you something like that? Let's think about it. We want something, so a real inductor, just a single inductor, right, would do what? A single inductor would look like this. On the Bode plot. So this is more than just an inductor. series, then it makes it flat at low enough frequencies, because this is basically just a short circuit. And at high frequencies, it basically becomes an open loop, but if I don't care about that, then I have to put something in parallel. So something like this, let's call this RA and RB and L, would give you that kind of general behavior. The question is, what are the values of RA and RB? Right? So let's start with the infinity value. At infinite frequency, very high frequencies, this branch is open. It's not there. So this is RB. And what is this? So I want to match this to that. I want to force this to be like that. Exact match. Behavior. So what is RB? What should RB be? Just for the sake of this kind of to keep this consistent with the handouts, let's call this RA and let's call this RA. So RA is what? R1. Exactly, right? What is RB? Well, let's look at it at zero frequencies. At zero frequencies, it has to be Rn. And what is this at zero frequencies? L doesn't matter, it's a short. So it's RB parallel R1. Has to be Rn. Which I can easily solve for RB. So then RB becomes Rm over R1. Let's solve it actually. So it's RB R1 minus Rm, RB Rm, check the factor RB out of, divided by R1 Rm. So this becomes, so RB is Rm times R1 divided by R1 minus Rm. Now, if Rn is much greater, if R1 is much greater than Rm, then RB is approximately or simply just R. Right? Now, by the way, look at this. This resistance can become negative. When does it become negative? When Rm is greater than R1, right? What does that mean? This negative resistance. It means that this model doesn't hold anymore. Because you remember the condition for this? The condition for this was that. So it means that it's not like that anymore, it's capacitive. So typically when you have R1 much greater than Rm, this is basically just Rm. Now to determine L, let's assume that to make our calculations easier. You can do the exact one, but you will get to the same result essentially. So let's just assume that this is simply Rm. And if you assume that, then the impedance of this thing, what is it going to be? What is the impedance of this? So if I ask you what is the impedance of this thing, how would you calculate it? Resist temptation to write KVL, KCL. So the impedance here is going to be what? Z0 when this value is zero value, which is what? The parallel combination of these two. And then it's basically plus, then you have Z infinity, which is R1 times the time constant. What is the time constant? Remember, we are determining an impedance, so we are putting a current source here. So this becomes open. So the time constant is R1 plus Rm times, or L over that, sorry. This is an inductor, it becomes L over Rm plus R1. This was an R1, right? Times S divided by 1 plus L over Rm plus R1 S. Now, I can rewrite this in a slightly different way that makes my life easier. So I can look at it and say Rm, R1, Rm plus R1, and factor this thing out. So this becomes R1 over Rm plus R1 times 1 plus, Rm plus Ls. Actually, let's take that out. Doesn't matter. Let's keep it this way. should have factored Rn. Let's do that, sorry. Because I have Rn up front. So if I factor Rn, I have so this is basically Rm. This becomes basically 1 plus R1 L over Rm R1 plus Rm S. And when you equate these, you can easily see that your L is simply Rm R1 C pi, or another way R1 C pi over Gm. Let me just do this exactly. Just a second. Just double check. Make sure I stay here. Yeah, if you make an approximation, basically the impedance becomes Rm 1 plus L over Rms divided by 1 plus L over R1 S. So if this is an approximation when R1 is much greater than Rm. And then you have to match these two. So if you match this one, for instance, you say L over Rm is equal to R1 C pi. Therefore, L becomes Rm R1 C pi. Or you can match this one, which gives you exactly the same result. Exactly the same thing. So that's your inductance. You calculate an inductance for it. So it's basically Rm R1 C pi. Very good. Okay, so that shows you what the output impedance of this thing looks like. It looks like an inductor in parallel, in series with the resistance, in parallel with another resistance. So it can have an inductive output resistance. Okay, let's do another example quickly, and then we'll move on to the next thing. The other example, which is another very common state that's used commonly, is the common source. So let's say this is R2, and this is R1, V out, V in. And again, let's think about one of the capacitors at this point in time. And we can do one or the other. So let's do C mu. Make it a little more interesting. So the question is, first let's determine the transfer function. The voltage gain, the function of time. So I'm interested in H of S, which is by definition VO of S divided by VI of S. And I know this is simply H naught plus H mu tau S divided by 1 plus tau S. So I need to determine the time constant, time and transfer constant. Well, H naught is what? Is the low frequency, the transfer function when the capacitance is 0 value. Basically, it's just a low frequency transfer function. What is it? What is the gain of this thing? Minus Gm R2. Or equivalently, you can write it as R2 over Rn. Now, H1, what is H1? Now, H1 is the transfer function when the capacitance is short. Infinite value. What does that give you? What is the gain? Well, if you're in doubt, this becomes a diode connected transistor, right? So you're basically shorting, if you think about the T model again, so you're shorting across here. So this is inconsequential. So it's Rn parallel R2 here, right? This is in parallel. So it's a voltage divider between this resistance, you can actually bring that down here. And this doesn't matter. And that resistor. Right? So it's simply Rm parallel R2 divided by 1 plus, R1 plus Rm parallel R2. I the resistance seen across here, what is that resistance? It's, you remember, let's go back to these expressions that we have. Oh, here. It's R left plus R right plus GM R left R right. So this is actually a simple case because since R3 is 0, this GM is the same as lowercase gm, right? This term is just 1, the denominator is 1. So it's just gm, so it's R left, which is R1, R right plus R right, which is R2, plus gm R left, R right. So it's simply R1 plus R2, which is R left, plus R right, plus gm R left, R right, which is exactly the same thing as that. This time, often we show this as R naught, right? So this is C mu R naught. We can show this as also R naught. Make our life easier. Okay, we are done, technically. Alright, so that we can put it together and see what it means. So let's put it together. So here I have, so let's just factor the H naught out. So if I do that, I get 1 plus H mu over H naught tau S, 1 plus tau S. So it's minus, I can even just keep it at H naught. I know it's minus GM. If I really wanted to know the value, I can go and check the value. So it's H mu divided by H naught. It's this guy divided by that guy. Now that I've written them in these forms, it's fine, right? So what is that ratio? The R2's cancel. So I get I get 1 plus Rm divided by R naught minus, exactly, thank you, times tau, which was R naught C mu times S. And in the denominator I get 1 plus R naught C mu S. And these R naughts cancel, so I just like to make it even simpler. It becomes 1 minus Rm C mu S. This is in the handouts. So I have a pole and I have a zero. It's expected. It's a first order system, the way I've shown it. What's my pole frequency? It's minus, so P is at minus 1 over R naught C mu. I can determine that. And what is my zero frequency? So it's a left half plane pole. And what about the zero? It's Gm over C mu. But it's a right half plane. Zero. See this minus sign here? So, and is it a low frequency one or a high frequency one? It's a high frequency. It's a very high frequency one because actually it's higher. Could be substantially higher than omega t because omega t is Gm over C pi plus C mu and C pi is typically larger than C mu. So this is more than a factor of 2 higher than that, but it's still there. So what you see is that you have a pole and then you will see this resistance. By the way, is this resistance small or large? The R naught. This resistance. It's relatively large, right? Because even if you ignore these first two terms, there's a GMR2, which is the gain, times R1. So this resistance is large. So actually there's a pole at relatively low frequencies, and there's a zero at some high frequencies. But it's a right half plane zero. parameters, you can always tell whether or not you have poles. These transfer constants tell you, I'm sorry, zeros, whether or not you have zeros, where they are, how many you have, and all of those. The same thing with poles. You can tell exactly how many poles you have, where they are, how many zeros you have, left half plate, right half plate, which one is larger than which one, and all those things. Without even doing analysis, without doing like writing equations, just by looking at the size of these things, relative polarities. So I could tell when I shorted this, the polarity, I changed the polarity of the transfer constant. Because when it was open, it was an inverting stage. When I shorted that, I made it a non-inverting stage. But here, when I open the stage, when I have the R2 here, when I open the capacitor, I didn't change the polarity of this. And that tells me that I have left. And I will do it more formally in a minute. Okay. Now, other things about this. So this stage, right now, the way I've drawn it is relatively simple, right? I ignore C pi. If I had C pi in there, also it would add some additional dynamics. And that would be taken into account later, but that's fine. But let me ask you another question about this. What is the input impedance of this stage? Now, I can do one of the two things. I can calculate the input impedance Z here. So, well, this is whatever Z here. But it's kind of like a little bit wasteful, right? And because I already have explicit resistor R1. So what really matters is this input resistance. Because whatever it is, then it's plus R1 gives you the other input impedance. So the intrinsic input resistance is what matters. What to be useful. So what do I do? How do I calculate? Let's do it. Let's analyze that. We'll see some interesting corollaries coming out of that. So what is the input impedance? Using again the same method. So what I'm trying to determine here, I've simplified my stage a little more, and I'm trying to determine the input impedance. If I were to determine the input impedance, I would apply a voltage source and I have a current source and measure the voltage. But then basically for low frequency stuff, I would put a current into an open. Because this is a MOSFET, right? So you can see probably my calculations, my life would be a little bit easier if I determine the input admittance up front. I mean, we know we can do both. So I try to determine the input admittance. Which is going to be Y naught plus Y mu tau S divided by 1 plus tau S. So I'm applying a voltage source here, Vx, and measuring Ix in the presence of C mu. So what are the values? What are the two? Let's determine the transfer constants first. Why not? What is the input conductance? Right, 0. Because the input resistance is what? Infinity. At low frequency, and the capacitance is nothing. So this is 0. Now what is Y mu? When C mu is short, what do you see?
1 over R2 parallel Rm.
Right, you see the parallel combination of Rm and R2. Right? The parallel combination basically in conductance domain is the sum of the conductances. So it's basically Gm, or 1 over Rm, plus 1 over R2. Fine? You can also write it as 1 plus Gm R2 over R2 if you want. And then, what is the time constant? Again, being careful, non-independent sources, in this case my independent source is a voltage source, so it becomes a short. So my life is a lot easier now, because my R left is 0. So R left is 0 plus R right plus R left, R right times Gm, which is also 0. So it's only R right that's left. So it's what's R right? Which is R2. So it's R2 C mu. So I'm done at that point. But let's do it, let's clean it up. So this is 0, that's fine. So I get, let's write this, you can write it different ways. 1 plus Gm R2 over R2 times tau, which is R2, C mu S, the R2's cancel. And then I have 1 plus R2 C mu S. So this is 1 plus GMR2 C mu S divided by 1 plus R2 C mu S. So I'm really interested in the input impedance. So when I'm done, I can invert it. So when I invert it, so Zn over Yn, which is 1 over Yn by definition, is going to be, so I will have two terms. I will have 1 over 1 plus Gm R2 C mu S plus, so it's 1 over that plus this over that, which basically cancels the C mu S, so I get R2 over 1 plus Gm R2, which I can write slightly differently. I just multiply by Rm. And then this is, I just recognize something. This is what? Parallel combination of Rm and R2. So I write it in the more meaningful way, because that way I can understand what's going on. Now, so what does the input look like? What is if I were to draw the equivalent input model for this stage, what do I see? What is this? The resistance. And what is this? What is that? It's just a pure capacitance, right? But it's of a different value. This capacitance is 1 plus Gm R2 C mu, and then there's a resistance in series with it, the ground, which is Rm parallel R2. Typically it's just Rm, close to Rm. And now if I had my C pi here, sitting here, that would be in parallel. But what has happened? So one thing that has happened is that the capacitance looks much larger, C mu, right? Now C mu has been multiplied by 1 plus Gm to R2, which is, by the way, what? Which is a DC gain, or negative DC gain, more accurate. So this is like 1 minus AB, C mu, or another way of writing it, 1 plus absolute value of AB times C mu. This is called the Miller capacitance. And we'll talk about it because this is called the Miller effect. So what's happening here? Why is this capacitance larger? Intuitively.
Well, it's kind of like feedback, right? So you have some gain from input to output, and then you're feeding it back in. So,
Well, you're feeding it back in, but what's exactly? So let's think about it. This side, massive marker now. Okay, so let's think about it. This. If this side goes up a little bit, let's say delta V, what will happen to that other side? This is an inverting stage, right? This will go down by how much? A times delta V, right? Minus the gain. So the capacitance, if the capacitance were connected to ground here, if you had a capacitance to ground from this node to ground, if the voltage changed by delta V, you would get some current delta I, some change in the current, right? Now, this side of the capacitor goes up a little bit, the other side goes down a lot. Breaks. Let's see if I have a better object. More solid. Okay, good. So, this is my amplifier. I'm moving this side up and down a little bit, and the other side is moving up and down a lot. So, the capacitance, which is sitting between these two ends, sees what? A huge swing. It sees exactly how much more? 1 plus absolute value of A. This much more swing. So the voltage across this is larger by this factor. Let's say the gain is 100 for the sake of it. So the capacitance, if you have a 1 millivolt change here, instead of it, if it were sitting across this point to ground, it would see 1 millivolt of change. And it would have some current corresponding change in the corresponding. But now it says 101 millivolt change. Because a little change here results in a lot of change there, and therefore it draws 101 times more current. So it's as if it's 101 times greater capacitor. And this is the intuitive meaning of Miller multiplication. example was not. So this is called a Miller effect. I'll have a side discussion about the Miller theorem, so-called quote-unquote theorem, and what's wrong with it in a minute. But the important thing to learn is to notice that this capacitance is m times larger. 1 plus a, 1 plus the gate times larger. And this multiplication is called Miller multiplication. So it was explained by this guy in 1920, Miller, and then basically he took his name. He never had a theorem, by the way. He never tried to prove a theorem or anything. Some people made it up. It's unfortunate because it's not wrong, which is not correct. If you want to make it correct, then it's not very useless. So, okay, so that's, now there's another thing here that would, I think, is as important and almost nobody talks about in this equivalent. Particularly if you're designing high frequency circuits or things that have significant high frequency, which is this resistance. This tells you that the input of a MOSFET, even if you had no gate resistance, nothing, nothing, just perfect gate, even that, it's not purely capacitive. There's a resistance there. Now, this is extremely important. This is real. This is a real resistance. There's a real part associated with it. Just simply you can see where it comes from. Now, this is important because if you make a MOS amplifier, a lot of times people try to match if you try to impedance match the input. Let's say you'll try to match a 50 ohm to the input of the gate of a MOSFET. Well, if it's a pure capacitance, there's no way you can match perfectly a 50 ohm to capacitance. And people may say, oh, I'm matching it to the gate physical resistance. Well, if you're doing that, then it means that you're just heating gate resistance and nothing else. No power goes into the transistor. You're matching this resistance, which is the power that goes into the system. And that's something that I haven't seen anyone else talk about, so it's good to know.
But you get some effects along the same lines by putting some inductance in the source too.
Okay, but why would you put an inductance on the source? Oh, you mean if you add an explicit inductance on the source?
Yes.
Yes, if you add an explicit inductance on the source, then you will get some real part in the input. And you will see that. You want to do problems.
Okay.
No problem. So, but maybe next quarter or something. But there's some problem with that effect.
Right.
Okay, so these are the two things. Now let's talk a little more about, okay, so there were a couple of questions, let's go over them.
I can see that how can you match capacitance in series with a resistor with another resistor? Is that possible? Can you explain?
Yeah, if you wanted to match it to make it purely a resistance, the easiest thing you could do is just like put an inductor and make this resonate that at the frequency of interest, right?
And then
it becomes real. Then you can match any real impedance to any other real impedance. I mean, you don't even need to do this. I just made this to make it simple. If one way to think about it, if you know a Smith chart, for instance, is that this is one point on the Smith chart, which has a real and imaginary part. So you can match it to anything that has a real and imaginary part. The problem is that if you just have pure imaginary thing, you can't match a pure imaginary thing to a real thing without inducing loss. And if you do that, then there's no power transfer. You can't transfer net power to an imaginary or term, which means that basically just putting constant power into a reactive element, which by definition cannot be done. Definition of a reactive element is that it doesn't have energy loss. So if you put more energy into the reactive element, just like its voltage amplitude keeps growing and growing, or the current amplitude grows and grows. Okay, you had a question?
So for the Miller effect, do you mean like instantaneously the circuit draw a lot of charge from
The capacitor draws this stuff, right? Because this side of it is going up, this side of it is going down, so it draws 1 plus absolute value of gain times more current. So it looks like a bigger capacitance, right? How can you draw n times more current? You have to have n times more capacitance, right? large time constant, which means that you have a slow pole. Because what you see, actually you can see it here too. If you look at this, I can rewrite it slightly differently. So I can write it as R1 times 1 plus GM R2. I'm dropping this term for the time being. Just it's an approximation. So if you just make it, just for you to see it, I mean, you can we'll deal with that later. C mu, right? This is a time constant. This is the Miller capacitance, right? As we defined it. So this is Cn. So you can see that the input time constant is R1 times Cn. So it's as if you have a capacitance of Cn here. With R1 you form a low pass filter essentially. You have to drops.
Physically, what does it mean? So it draw current, draw charge from gates.
No, draws charge from your input, from whatever source is, or in this case it will draw current out of R1. So it needs a lot more current. It wants a lot more current here, because this current is 0, right? So whatever current this guy draws has to come from here. So that resistor has to be smaller to be able to provide the same current without dropping the voltage.
So leakage?
No, it's not leakage. It's just basically, it means that as you increase the frequency, the gain gets killed because more of your voltage drops across this guy, and less of it gets there. So it means that your gain starts dropping faster. It means this. Any other questions? Yeah.
Like in this case, you have C equals to 1 over Y. Is it because you're using a voltage source?
No, this is always true. This is always true. This is the definition of C and Y for one port, for a single port element, right?
Okay.
If you have Y in and Z in, if nothing else has changed elsewhere in the circuit, they're the same. So I can calculate this input impedance as a Y in or as a Z in. Now, Y calculation was easier in this case. So admittance, I did it admittance calculation. But if you have to be just careful to see which one you're calculating. In this case, I was doing it admittance calculation, so I put a voltage source. Because admittance is defined as the ratio of a current to a voltage. So my stimulus has to be a voltage.
So does that mean that when you calculate for impedance, you have to use current source?
Right, exactly. If you're calculating an impedance, then you have to use a current source. So basically, whichever one is easier for you, if for instance, if you see that, okay, if I put a voltage source, then it defines this voltage to make my life easier, you're welcome to do that, but you're calculating an admittance. So remember at the end, just keep everything consistent. Once you calculate your admittance, just invert it. Okay. So this is clear, right? So let's go back and talk a little bit more about this Miller theorem.